In this video, we are continuing with Lewis structures, and we are going to look at expanded octets and resonance. Have your periodic table handy as you take your notes. Up to this point, we have looked at exceptions to the octet rule with incomplete octets. In other words, when atoms become stable with less than 8 electrons in their outer energy level. Now we will look at atoms which can be stable with expanded octets. In other words, more than 8 electrons in their outer energy level. These would be the nonmetals in energy level 3 and above on the periodic table, beginning with phosphorus. These can support more than 8 electrons when they are central atoms and remain stable. They use their d orbitals to support further bonding. And these are called expanded octets. Some examples would be phosphorus pentachloride, sulfur hexafluoride, iodine heptachloride, krypton tetrabromide. If we look at some of these structures, there is phosphorus as a central atom. And if we count the electrons around it, there are 2, 4, 6, 8, and 10 electrons around this phosphorus. So it's more than 8. Sulfur over here as a central atom has 2, 4, 6, 8, 10, 12 electrons and can be stable. Let's practice some examples. Krypton tetrabromide. We find out how many valence electrons are available for bonding. Krypton has 8. Bromine has 7, and we have 4 bromines, so 4 times 7, for a total of 36 available electrons. We start drawing the structure with krypton as the central atom, bonded to 4 bromine atoms. We make each peripheral atom have 8 electrons. So we have 2 in the bonded area here, 3, 4, 5, 6, 7, 8. And the same thing for each bromine around the krypton. When we count how many electrons we have used out of the 36 available around each bromine atom, we find that we have 8 plus 8 is 16. Plus another 8 is 24, and the last 8 is 32. So we have used up 32 electrons, but we said that we had 36 available, so we cannot throw 4 electrons out the window. What we do is we add these 4 last electrons in pairs as usual around the central krypton atom. So we are going to add 2 here, let's say, and another 2 over here. Now we have added 4 more, so we do have our total of 36 electrons in the molecule. So I have redrawn krypton tetrabromide neatly, and we can see that the central krypton atom has 4 bonded pairs of electrons, which makes 8 electrons, and 2 lone pairs of electrons around the central atom. And this is the final structure for krypton tetrabromide. Let's do one more example. Iodine pentachloride. Let's look at the valence electrons available. Iodine has 7 valence electrons, and chlorine also has 7 valence electrons, and we have 5 chlorine. So a total of 42 valence electrons are available. If we draw the structure, we are going to draw iodine in the middle, and 1, 2, 3, 4, 5 chlorine atoms around it. Now we give each peripheral chlorine an octet, so we have 2 in the bonded area, 3, 4, 5, 6, 7, 8, and we do the same thing for each chlorine atom, so that they all have an octet. Now again, if we count how many electrons we have used up out of the 42, we have 8, 16, 24, 32, and 40. So we have used up 40 out of the 42 electrons. So we have to put an extra pair of electrons on the central atom, which would be iodine. So we can put it, let's say, over here as a pair. We can see that the central iodine atom over here has 2, 4, 6, 8, 10, and 12 electrons around itself. It has 5 bonded pairs and 1 lone pair of electrons. Let's talk about resonance. Resonance occurs when more than one valid Lewis structure can be written for a molecule. It could also be for a polyatomic ion. The actual structure is an average of all the resonance structures. So when there is resonance, you must draw all the possible structures to be correct. Let's practice with the nitrate ion. The formula for nitrate is NO3 with a negative charge. Let's look at the available number of valence electrons. Nitrogen has 5 valence electrons. Then oxygen has 6 valence electrons. And we have 3 oxygens. And then we have to account for the negative charge. So this has gained an electron. So we are going to add 1. So the total number of available electrons will be 24 for nitrate. Then we draw the Lewis structure as usual. Nitrogen in the center with 3 oxygen atoms around it. We make each oxygen have 8 electrons. And we check if that makes up 24. We have 8 plus 8 plus 8. So we have 24 electrons accounted for. But if we check octets, this oxygen is happy with 8. This one has 8. And this one has 8. So they are all satisfying the octet rule. The nitrogen, however, only has 6 electrons around it. So it is not yet satisfying the octet rule, and it has to. So we are going to form a double bond by transferring 2 of the oxygen electrons here to the bonding area. So our structure instead will be nitrogen. With the 3 oxygens, we have a double bond here. So 2 lone pairs are left. And the other oxygens have 3 lone pairs each. So now all of them have 8 electrons and nitrate is happy. We have to remember to put the square bracket with a charge of -1. Now, instead of having picked this area to form the double bond, we could have also formed the double bond over here or over here. So there are 3 structures that we can draw to represent the nitrate ion. So this is when we have to draw resonance structures. So we put an arrow pointing both ways and we redraw the nitrate ion, this time with the double bond over here. And we close the bracket and keep the charge. And we draw the 3rd resonance structure, this time with the double bond on the left. And we close the bracket and put the charge. So these are the 3 resonance structures for the nitrate ion. And you have to draw all 3 to be correct. So let's recap resonance. We said that resonance occurs when more than one valid Lewis structure can be written for a molecule. Later in this unit, we are going to learn about bond length, but for now we will say that a single bond is longer than a double bond. The experimentally calculated bond length of the nitrogen-oxygen bonds in nitrate is somewhere in between that of a single and a double bond. And it is measured to be about 1.33 times the predicted bond length of a single NO bond. So it is somewhere in between the length of a double bond and a single bond for all three of these bonds. Scientists now know that nitrate actually has a single structure, which is the average of the three structures that are drawn above. And together these structures are referred to as resonance structures or sometimes resonance hybrids. This is why we must draw all the possible Lewis structures to correctly represent a molecule or ion with resonance. This concludes our fourth video. Come to class prepared with your notes, please.